All right, now we move towards the whole theme of the chapter, which is this concept of electric potential. And again, I totally hear you. You're like, didn't we just talk about electric potential energy? What is this electric potential? Yes, they're different, but they're related. And I'm going to explain how. So it turns out that talking about potential energy for various reasons is problematic, or just a little bit more complicated, I would say. Not problematic, just more complicated. And it makes a little bit more sense, a little bit easier to think of a quantity that's called the electric potential, that is the amount of electric potential energy per coulomb, per unit charge. Okay? So this is like saying, all things being equal, how much energy is there per charge, not how much energy per particle. Okay? And that kind of levels the playing field a little bit, and it makes it a little bit more easy to look at electricity from a big general standpoint. Once again, I want to say many, many books will have the potential energy be U, so I'll put that there too. So electric potential, V, which is measured in volts, which is also just V, is just the amount of potential energy per coulomb that a charge in that electric potential will experience. Okay? And so the most simple version of electric potential is the electric potential of a point charge, as we've seen so far, right? We've found the force due to point charges. We found the electric field due to point charges. And now we're going to talk about the electric potential due to point charges. And I'm going to tell you that it's actually quite familiar. So the electric potential due to a point charge is just K times the charge of that point charge divided by R, how far away you are from that point charge. Okay? So what does that mean? It means that if I over here have a positive charge, okay, then at every distance r away from that charge, and let's say it's charge q, every distance r away from that charge will have a certain potential that's equal to k times q divided by whatever that r is. Okay? That means that for every distance r, you're going to have one common potential all the way around. All right? So that'll look something like this. So at this distance r, at every point along this r over here, you're going to have one potential. Okay? At this distance r over here, you're going to have another potential, right? And you would expect that the closer you get, in other words, the smaller r gets, the closer you get to this charged particle, the bigger V is. So really up close, you might get a potential of, let's say, 100 volts. Let's just make it simple, right? We choose some Q and some R so that that's 100 volts. And then here you might get like 50 volts. And then here you might get like 25 volts, right? And then out here, you might get like 5 volts, right? And then at infinity, when R is equal to infinity, then you get 0. So you don't get 0 voltage until you're all the way as far as you could possibly be away from this charge, all right? So pretty simple. The other thing that I want to add to that is that the electric potential is just a scalar. And if it's just a scalar, it means when you add potentials, you don't, again, have to worry about adding any kind of vectors or take into account any angles, which makes life a lot easier. You'll find that dealing with electric potential is probably a little bit more convenient than dealing with electric fields. So a while ago, I told you that electric potential is another way of explaining why charges move in and around other charges. Okay? So I'm going to use electric potential to explain this. So if I put another charged particle here, okay, if that charged particle is in a potential field, it is always going to want to move from high potential to low potential, right? So it's almost like a hill. So I could redraw this as I have a charged particle here, okay, and it's like right here at 0, right when you're right next to it, it's like being at the top of a hill, right? And the farther away that you get from it, that hill is going down. So this will be like the 100 volts up here. Here's like the 50 volts. Here's like the 25 volts. You know, and then at some point far away at infinity, you have 0 volts, right? And so what happens is, if you have another proton that's at the 100 volts, it wants to roll down, right? In other words, you can almost think of it like a topographical map. And in fact, in this slide, I do have a topographical map that shows this better than I can draw it. So look at that and see how it's almost as though these equal potential lines, by the way, these lines where everything is at the same potential, not surprisingly, they're called equal potential lines. So these equal potential lines, a positive particle is going to want to move down them, roll down them in the same way that a ball is going to want to roll down a hill. All right, I hope you can kind of see that analogy. Obviously, there isn't an elevation here. There isn't actually an elevation. You can just think of these higher voltages as being at like a higher elevation, and the ball is just rolling down it. So positive charges, that's the first thing you want to write this down because this is key. Positive charges want to move from high potential to low potential. Always, 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 right? So if you ever have a potential difference, all right, where in other words, you have a potential field and there's two areas where there's different potential, a charged particle, a positive charged particle will move from the higher potential to the lower potential. That's just how it works. That's how nature works. And it's kind of an easy way to think of why particles move. If I have another field here where everything's at 25 volts everywhere, right? So everywhere you look, it's all 25 volts, 25, 25, 25. And I put a positive charge there. What does it do? Nothing, because there's no potential difference. But if you do have a potential difference, in other words, a delta V, right? From here it's 100, here it's 50, so that the delta V would be 50. It's going to want to move from the higher potential to the lower potential. Just like if a ball is on a flat surface, it doesn't want to roll. But if you have the ball on a curved surface, it wants to roll. Does it make sense? If there's a delta H, the ball will roll. If there's a delta V, the charge will roll. Okay. This analogy is helpful for me. I hope it helps you too. The one place where the analogy gets kind of freaky is that if I now have a negative charge in that potential field, okay? Obviously, we know negative charges are attracted to positive charges. So negative charges roll uphill, okay? So in gravity, we don't have negative masses, so we never see balls rolling up hills, right? But in electricity, since we do have negative charges, we actually see electrons moving from lower potential to higher potential. So that's key. Positive charges always want to move from higher potential to lower potential, all right? They accelerate, they gain energy if they move from higher potential to lower potential. Negative charges always want to move from low potential to high potential. That's their natural instincts as little negatively charged particles. All right?